Okay, so hello. My name is Eli Park, and this is the slides were made by Pranav, Konda, and Eli Park, and today we will be going over radical axis and center. So let's review power of a point. So recall that the power of a point of a point P with respect to a circle omega with center O and radius r is defined as OP squared minus r squared, and we denote it. Let me get my pen up. We denote it like this. So thus, we have the power of a point theorem. If a line drawn through a point P intersects the circle, omega at points A and B, then the power of point P with respect to omega is equal to PA times PB. So these lines are directed, meaning that if rays PA and PB are point opposite directions, then the power of point P should be negative. And also note that A and B can be the same point if the line through P is tangent to the circle omega. So we can now state the radical axis theorem, which says, given two circles omega 1 and omega 2 with distinct centers, the radical axis of the circles is a set of points P such that the power of P with respect to omega 1 is equal to the power of point P with respect to omega 2. And we can now state the radical axis theorem, saying let omega 1 and omega 2 with distinct centers O1 and O2. So then the radical axis of omega 1, so in this diagram here, we'll let this be omega 1 and this be omega 2, is a straight line perpendicular to omega O1, O2. And if these two circles intersect at 2 points A and B, then the radical axis is the line AB, this line itself. And almost always when we deal with radical axis problems, you're going to have two circles that are intersecting. And this may not always be the case, so you will have to be look out for other cases, but you can basically almost always assume that you're going to be dealing with problems that deal with this theorem deal with intersecting circles. Now we can state the radical center theorem. The radical center is a point at which the three pairwise radical axes of three circles concur. Sometimes the three radical axes, within this diagram, we see that with these three circles, one of them is dotted, it's supposed to be used for later. We see that we have radical axes, if we let these points be, let's just let these points be E and F. We see that AB is a radical axis, EF is a radical axis, and CD is a radical axis, and they all intersect at a point P. That point P is the radical center, and it must exist. So these three radical axes must concur as long as the three circles have centers that are not on the same line. Wait. Yeah. And they must be separate, yeah. So now we can have the following result. If points A, B are on omega 1 and omega 2, and CD are on omega 2, then the following are equivalent. If A, B, C, D lie on a circle such that the three centers aren't collinear, and A, B, and C, D intersect on the radical axis of omega 1 and omega 2. So what I mean by them being equivalent is that if one is true, then the other must also be true. And if one is false, then the other must also be false. So we can see here, we have a visual aid basically. If the first one says, if this dotted line is true, then they intersect at a point P which lies on the radical axis. And the other way around, if these two lines intersect at a point P, then they're cyclic. And generally, the other way around, so the second one I just stated, is more commonly used, where you know that this is true, and then you use that to show that this is true, and then you use that going forward. So let's start with an example. So given circles omega 1 and omega 2 intersecting at points x and y, let L1 be a line. So before we get started, I'm going to draw a rough diagram because normally that's what I like to do. I like to freehand a diagram while I'm reading the problem just to get an idea of what's going on. So I'll draw two very rough circles. I'm not used to drawing circles on here, I apologize. They intersect at points x and y, and let point L, you know what, I don't like this diagram because the center of this circle kind of looks too much on the other circle. So let me draw a new diagram. Oh well, we kind of have points sticking out, but it doesn't matter. It'll do this enough. So there's a line L1 that goes to the center of omega 1, this be omega 1 and be omega 2, and intersects omega 2 at points P and Q. We know points P and point Q, and the other way around also works. Other way around. So this intersects at R and S, and if we're trying to see if P, Q, R, S, so in red, P, Q, R, and S are cyclic, then the center of the circle lies on line XY. So now we can already tell here that without actually solving the problem, we can see that we can start trying to think about, because we know that XY is a radical axis, we can try to think about it in that direction here without actually, before we get started. So now let's look at an accurate diagram. When you're solving the problem, obviously you would draw a more accurate diagram and take the time to do that, but I just have it set up here. So let's start, so here's a solution. So do note that PQ is a radical axis of omega 2, omega 3. We should see that because, PQ are the two intersections, and that RS is the radical axis of omega 1 and omega 3. So, so let me go to say the first one again. PQ is a radical axis of omega 2 and omega 3. And we see that O1 lies on the radical axis. So we can get this first statement by the definition of power of a point. We know that the power of a point of O1 with respect to omega 2 and omega 3 are the same. So we get that first equation. And doing the same thing, just by switching omega 1 and omega 2 and O1, O2, gives us the second equation. Because you see that RS here is a radical axis, and we get O2 lies on it. So it's the power of a point with respect to of O2 with respect to omega 1 and omega 3 are the same. So subtracting these and just rearranging the terms, you're gonna get this. Oh gosh, I did not mean to do that. You're gonna get this. And this looks very familiar too. So, and this is in fact saying that the power of a point O3 with respect to omega 1 is equal to the power of a point O3 with respect to omega 2, which is the same thing as just saying O3 lies on the radical axis of omega 1 and omega 2. But the radical axis of omega 1 and omega 2 is xy, so O3 lies on xy, and we are done. So next problem. So I'll be drawing the diagram while I'm reading the problem. So let A, B, C, D be 4 distinct points on the line in that order. Okay. So I'll draw A, B, C, and D. C looks in the middle of D, the BD. Draw it a little bit off. Yeah, something like that right there. Looks good. So we have two circles with diameter AC and BD. I'll draw very rough circles. Oops. I'll erase that one. It didn't look good. Yeah, this is not looking hot. This circle's not going to fit, but I don't think it's very relevant, the rest of that circle. So, because we'll just deal with the top part of the diagram and intersect our words. So to intersect at X and Y, and that meets line BC at Z. Yeah, I should not do that. I have a bad habit of just like sketching it like that. And the line CP, sorry, I'm getting ahead of myself. So P is a point on XY other than Z. We'll work it up here because the bottom part of the diagram is kind of closed right now. And line CP intersects the circle at C and M. So this is M, and BP intersects the circle at N. We're trying to prove that AM, DN, and XY are concurrent. And you can see that they're not concurrent because my diagram is obviously very, very off. But we can start thinking here that these concurrencies and these intersect and the use of the line xy really looks familiar to our radical center theorem. And if there was a way that we could get A, M, and D is on a circle, then we can see that A, M, and ND are also radical axes. And we can somehow get that this concurrency is a radical center. And so yeah. So let's look at this accurate diagram that I've set up on GeoGebra. So yeah, just take the time, look at this, and now we'll start getting into it. So by the radical center theorem, so let's go back. We see that, actually let's not go back. We see that these two chords BN and MC intersect at a point P, which lies on radical axis XY. Well, by our earlier this theorem down here, this implies that this is true, which means that this must also be true. So going back, we know that B, C, and M is cyclic. And although this isn't the cyclic quadrilateral that we want, this will help because by angle chasing, we then get AD and M is cyclic. And that is, we're just chasing angles using our cyclic property, B, C, and M. This left as an exercise for the reader, for the viewer. And then once we get AD and M is cyclic, we see that the lines XY is a radical axis, our three pairized radical axes will be XY, AM, and DN, which means that they concur at a point, which is a radical center. And since the radical center must exist, since we see that AM, XY, and DN are concurrent at this magical point. So yeah, so that was it for this lecture. And if you would if you are currently not in CNCM right now, join us. There are more details at cncmath.org. And if you were viewing this and an aid for your POTD, good luck for this week. And see you guys next time.